Hi guys, in this video we are going to talk about decision trees and give an intuition into what they are and how they can be used for classification and regression. So decision trees are a graph structure which consists of nodes that split into children nodes. Most often in the context of decision trees, we will refer to binary trees. These are trees that only have two child nodes per parent, though there are also non-binary implementations, but I won't get into them for now. To use decision trees to make predictions on our data, we will split the data on some X feature or predictor to predict the Y value, the response or label. This is done one feature at a time. This can be used for both classification, for example, left node is class A and right one is class B, or regression, for example, left is 5.5 and right is minus 3.1. Let's establish some terminology. There are different types of nodes, which are these oval things here in the graph. You have the root node, which is the top node that is the first node that splits the data. This node is the child of this node and also the parent of this node. Some nodes have splits, but some are terminal or leaf nodes and only contain the final prediction. The edges refers to these arrows here, which are sometimes also called branches. Splitting or partitioning refers to both partitioning the feature space and the data that flows through the tree using some decision rule, like is x less than or equal 10. Splitting is done according to some criteria or metric. For example, here we split by x less than or equal to 10. We choose it based on some criteria. What criteria we will see later on. The depth of the tree is the number of levels it has. If we start counting the root node as 1 and we also include the leaf nodes, then this tree has a depth of 3. The nature of trees make them so that the space is always separated into boxes. Each decision rule has two options, true or false. In 1D space, this will translate into different cutoffs, creating 1D regions. In 2D, we will have axis-aligned lines creating rectangles. In 3D, axis-aligned planes creating boxes, and in 4D and more, axis-aligned hyperplanes creating hyperrectangles or hyperboxes. In this plot, you can see a classification problem where X is two-dimensional. The decision boundary is always this non-smooth composition of straight lines in this rather jagged manner. Let's follow an example of classification in 1D. We have some data on the x-axis, and it can either be labeled red or yellow. The tree looks for the best split and finds that it's on asking if x is smaller or equal than minus 7 or not. If it is, we reach a leaf node and can label the points red. If not, we reach a split node and look for the next best split on the remaining data. We find that x less than or equal to 2 is the best criteria and we split again. We continue on until we either reach a perfect classification or some restriction which we can impose on the trees, but we'll talk about them later. Here is a similar example in 2D. We have some 2D data. We look for the best split and find that it's if x1 is less than or equal to 5. If it is, we look for the next split and find that it's x2 less than or equal to 3. And we label accordingly. Likewise, for x1 greater than 5, we find the best split to be x2 less than or equal to 4. Now let's move to regression. We have the following data, and we try to predict the y value for each x. In this tree, we first split at 7, then find that the next best split is at 3 and 11. If x is less than 3, we give the value 2. This is the mean y value of all the data points in this bin. We continue and do more splits until we finally get this red regression line. You can see it is also very jagged. But how do we build a tree? How do we find the best split, which feature to use, and which cutoff point for the feature? We will look into it in the next video, but in a nutshell, we will do this based on some metric. For classification, we will mainly use impurity coefficients, and for regression, we will measure the variance of the y's in each node. We will look for the split that improves these metrics the most. But this is all for this video. See you in the next one.